Today we are learning about solutions. Right? So there are two parts to a solution. We have the solute and then we have the solvent. The solute is the substance that is being dissolved. The solvent is the substance that is doing the dissolving. Right? So in terms of solubility, now remember, solubility is the ability of a substance to dissolve in a solvent, right? It tells you how much of that solute will dissolve in the solvent. Solids generally become more soluble as you increase temperature. So for example, for example, if you have hot tea versus iced tea, if you try dissolving sugar in both, the sugar is going to dissolve a lot better and faster in the hot tea than in the iced tea. Anyone who's ever drank iced tea, when you try to dissolve sugar in there, you have to stir it up a whole bunch, to make it sweet tea. Right. Gases generally become less soluble as the temperature increases. So gases actually will dissolve better when the temperature is lower. All right. An example here is as ocean temperatures rise, the oxygen gas that's dissolved in the water becomes not dissolved anymore. Okay. As the temperatures of those oceans increase, less gas stays dissolved. And what happens to the fishies? They die. And it's really sad. Yeah. No, that's literally what happens. When the oxygen goes away, they no longer have that oxygen dissolved in there to live. They don't.
They swim away.
Yeah, they might migrate away, but it will decrease the population because if there's less of them that can live there. Yeah. There's also ocean acidification that occurs as temperatures rise, but that's something different going on. All right. So now we're going to talk about a couple different ways to quantify the concentration of a solution. There are several ways to calculate concentration, several different types of concentrations. We're going to learn two, okay? And they're called molarity and molality. I know, it's frustrating that it's literally a one-letter difference. Molarity is the main one we're going to use. That is moles of the solute divided by liters of the solution. So we need to know how many moles of solute we have. Sometimes you're given grams of the solute, which you would need to convert to moles. Remember, nothing ever goes away in chemistry. And then the bottom, liters of the solution, that's the total liters of the entire solution. Okay. So let's look at a couple examples. A solution contains 0.90 moles of NaCl in 0.50 liters of water. Calculate the molarity. Which substance in this problem is my solute? NaCl, that's the substance that is being dissolved. So sodium chloride, NaCl, that's my solute. And therefore, what does that make water? The solvent. The NaCl dissolves in the water, forming the solution. So, in order to calculate molarity, we're going to take 0.90 moles and divide it by the volume in liters of the entire solution. Well, we can actually just use the volume of the solvent as the volume of the solution because the solvent is in a much larger quantity than the solute. And so the little bit of solute we're adding to this is not enough to change the volume. So the bottom number, the liters of solution, will just be the volume of the solvent. And that's 0.50 liters. Okay. So go ahead and do that calculation, and we're going to get the concentration. What do you get? You should get 1.8. Now let's talk about units. You can write the units as moles per liter, because we did moles divided by liters. The label is always whatever the solute is. Okay, so our label here would be NaCl. Now there's another way to write that unit. Molarity has a symbol. You can leave it as moles per liter, or you can write it as a capital M. So that's another way you can write the unit. I don't care which one you use, but please be aware that if you use big M, you still need to know that that means moles per liter. Okay, just pick one though. Please don't do both, because sometimes you might write it wrong and then you lose points. If you had just left it with whatever you originally wrote it as, you'd be fine. Okay, but easy. Okay. All right, let's look at the next one. We have a solution that contains 1.2 grams of MgCl2 in 100 milliliters of water. Calculate the molarity. So what's my solute for this problem? MgCl2, that's the thing that's being dissolved. And therefore water is the solvent. Unless it's a weird problem, if water's in the problem, it's almost always going to be the solvent. For your class, like for this class, I'm not going to give you any problems where water, if water's in the problem, it's the solvent. There are circumstances where water isn't, where it's actually the solute, but we're not going to see anything like that, right? So if water's in the problem, it's going to be the solvent. And most of the things we're going to be doing are going to be ones where water is the solvent. Okay, but there are going to be times when we might have some example problems where something else is the solvent. You have like sodium chloride dissolving in like acetic acid or something like that, but those are rare. Okay, but water is pretty much, it's called the universal solvent for a reason. All right, so in order to do the molarity here, we need moles of the solute. Do we have moles of the solute? No, we're given grams of the solute. So how do I get that to moles? Mole conversion using MM on the PT. So I'm going to take 1.2 grams of MgCl2, and I need to convert that to moles. So I need the molar mass of MgCl2. So somebody needs to calculate that for me. Bless you. 95.21? That sounds right. So how many moles of MgCl2 did I put in the 100 milliliters of water? How many moles is that? Point 0.01. 0.013 moles of MgCl2. Remember, we need to maintain sig figs. 1.2 has 2 sig figs. 0.013 has 2 sig figs. Those zeros at the front of the number don't count for significant figures. Okay? Ow. So now I have the moles. What am I going to divide that by? I'm not going to divide it by 100. Nope. This 100 is in milliliters. I need it in liters. So I'm going to divide it by, what's 100 milliliters in liters? 0.1. And then for sig figs, 0.100 liters. So make sure you go back and review your metric conversions. The most common ones we do use are the base units, liters, meters, grams, those types of things, and then milli and kilo. Those are like the most common ones we use. You learned a lot more, but those are the most common ones. So what is that? 0.13. And what's our unit? You can write it as moles per liter or as the big M. I don't care. And what is our label? MgCl2. Whatever the solute is, that is the label. Okay? All right, the next problem is we're kind of working backwards. So we're told the molarity, we're told that we have a 0.40 molar solution of glucose. So since we're saying it's the solution of glucose, glucose is my solute, okay? And that contains 8 moles of the solute, and we want to know what is the volume of this solution. So remember, molarity is moles per liter. So I can kind of set it up like a math problem. I know the molarity. I'm solving for the liters. So I'm going to put that in as my x. Okay. And if the units throw you off, if the units like make it confusing, get rid of them for the sake of doing the algebra and set it as 0.4 equals 8 over x. How are you going to solve for x? What? One way to you need to get x out of the denominator. So if you cross multiply and then divide, you end up setting it as x equals, 8 over 0.4. Like when you rearrange that formula, you get x equals 8 over 0.4. So x is our volume. So what is 8 divided by 0.4? You get 20 liters. How are we going? Do we have the? Oops. Yeah. Do we have the appropriate number of sig figs? How are we going to make the appropriate number of sig figs? Put a decimal point at the end, right? Because we need to have 2 sig figs. You could also have put it in scientific notation. If you wrote it as 2.0 times 10 to the first liters, that's one way to deal with significant figures. It's weird. All right. Questions on these? That's molarity. That's going to be the most common concentration stuff we use. The colligative property stuff, which we may or may not get to today, depending upon time, that uses the next type of concentration that we're going to learn, which is molality. Okay, molality, I meant to box this. Molality and molarity are very similar, both in name and in how you calculate them. Right? Molality is moles of the solute on the top, just like molarity, but we're dividing by kilograms of the solvent. So moles per kilogram. So solute always goes on the top because it's always talking about how much of that solute for the whole thing or how much of that solute per the solvent. Molality also has a symbol for it. Like molarity was a capital M. Molality is a lowercase m. I know it's frustrating. However, when I type a lowercase m signifying molality, I'll put it in italics, so it's kind of slanted. When I write it by hand, I kind of do it in cursive. Make it like a fancy baby M. Okay. All right, so let's run through some of these problems. So a solution is prepared by dissolving 0.500 moles of NaCl in 1.000 kilograms of water. What is the molality of this solution? So just like before, let's identify the solute and solvent. What's my solute?
NaCl.
NaCl. Which makes water the solvent. All right, so molality is going to be moles of the solute, 0.500 per kilogram of the solvent, 1.000 kilograms. This math should be really easy. What's 0.5 divided by 1? 0.5, right? But we have to maintain sig figs. How many sig figs are we going to have? 3, because that's the lowest number from the problem. And then we can either write the units as moles per kilogram. Our label would be NaCl. Or we can write it as a little m. Okay? Questions on that one? Let's look at the next one. I'm going to change one thing just for sig fig purposes. I'm going to make this have 100 kilograms of water versus 100 kilograms of water. So this is going to be the exact same way. We're going to take the 1.5 moles of NaCl, because that's my solute, over 100 kilograms of water. So go ahead and calculate that. What is 1.5 divided by 100? 0.015. And then the unit, you can either do moles per kilogram or the fancy baby M. And our label, regardless of how you write the unit, the label will be NaCl. Questions so far? It's very straightforward. It's just a lot to remember. All right, number 6 is like number 3 from the molarity problems, where we're given the molality, we're given the concentration, and we're given a component of it, and we're trying to find the other one. Okay? And again, just like with the last one, I'm going to put a decimal point at the end of 500 grams to make it not have one sig fig. Okay. So molality is moles per kilogram. I know the molality, I know the kilograms, I need to find moles. Okay? But this problem is actually asking me to find the grams of potassium iodide, so I'm going to go from moles and then convert that to grams. Before we actually find the moles, what's the chemical formula for potassium iodide? Ki. Potassium is +1. Iodide is referring to the ion of iodine. So it's I-1, so it's Ki. It would be KiO3 if it was iodate. Okay. All right, so we're told that it's 0.060 molal. That equals, how many moles of Ki are we using? We don't know. That's what we're asking to find. So I'm going to put that as my X. And I'm using how many kilograms of water? 0.5, not 500, because that was in grams, converted to kilograms. How are we going to solve for X for this problem? Yep, you're just going to multiply 0.06 and 0.5. So what do we get as our X? 0.03? And I heard you say it with proper sig figs, 0.030. And that's moles of Ki. Now how do we find the grams of Ki? Mole conversion, converting moles of Ki to grams of Ki. So we need the molar mass of Ki. Potassium has an atomic mass of 39.10. Iodine is 127.60. So you're just going to add those two values together. And you should get 166.70. Which you take that molar mass and you multiply it by the 0.030 moles that you have of this solute, and you should get how many grams you should actually dissolve in that 500 grams of water. Well, with proper wait, hold on. 0.03. 0.03. You did 0.3. What is it? 5.0 grams because of sig figs, and then Ki. So for the 500 grams of water, we would need only 5 grams of potassium iodide to give that 0.040 molal solution. All right, so that is molarity and molality. We're going to do one more thing in terms of calculating with solutions, but this is not a new type of concentration. It's more of when we want to change the concentration. Okay. I'm going to pause for just a second because I need to get something available. All right. So like I said, the next little bit we're going to do has to do with changing concentrations of solutions. More specifically, diluting solutions. So when you want to make a solution from a specific concentration that of that solution that you already have, you're always going to be diluting it. And you're going to dilute it by adding more solvent. It's really difficult to take a solution, and if you need a higher concentration, to do that. Because trying to remove a solvent from an existing solution is difficult. One way to do it, you could heat it, but you can't, it's hard to regulate how much you boil off of the solvent. So much easier to go from a higher concentration and diluting it down to a lower concentration by adding more solvent. All right. So the formula we're going to use is M1V1 equals M2V2. It's similar to some of those gas laws we used, but M stands for molarity. Those big M's stand for molarity, and V stands for volume. A big hint that I'm going to tell you that will make your lives a lot easier with all these formulas, or with this formula, is set M1 to be your greater concentration. Set that to be your high concentration, and M2 is the concentration you're diluting to. All right? You're almost always going to be solving for V1, because you're almost always going to need to calculate how much of that higher concentration you need in order to dilute it down to the concentration you're almost always going to be calculating the amount of the higher concentration you have and diluting that down to the concentration you need, which will be a lower concentration. Okay. The device we use is this thing, which I also have right here. Does anyone remember what this device is called? Flask is almost correct. It's just not specific enough. Volumetric flask. It's on your notes packet. It's like written right here. It's written right here. Okay, volumetric flasks. If you look on the image on the board, or if you look at the one I have in my hand, how many graduations or lines are on that flask? There's only one on there. There's only one. That one line is specifically, like that, it only can measure to one volume, okay? The one on the board, what volume can that volumetric flask measure to? 50 milliliters, which is why it says 50 milliliters on the flask. The one in my hand can measure to what volume? 500 milliliters. So the line, I'll use the one on the board for the sake of the video. This line measures at exactly 50 milliliters. Plus or minus maybe like half a milliliter, but it's very, very, very precise for that one volume. Okay? So it's really beneficial. Like volumetric flasks are used to make solutions. Like that's its main purpose, okay? That's what they were designed for, right? Was to dilute solutions and make specific, precise concentrations, or as precise as possible, concentrations of solutions, right? So like if I needed 25 milliliters of this solution, I wouldn't be able to use a 50 milliliter volumetric flask because I don't know where 25 milliliters is. I mean, yeah, you could try to eyeball about half, but you're not going to get it. It's not going to be exact. Whereas 50 milliliters, that's really exact. So you want to make sure you use the appropriate size volumetric flask. All right, I'm going to go back to this. Let's go through a couple problems. We want to know how would we prepare a solution, 100.0 milliliters of a 0.40 molar MgSO4 solution from a stock solution of 2.0 molar MgSO4. All right, so my formula is M1V1 equals M2V2. Let's identify those components. What will be my M1? We're going to use the higher concentration, so that'd be 2.0. And remember that M stands for molarity. So what would be my M2? Yep, the 0.4. Do we know how much of the 2.0 molar I need to measure out? No, that's what I'm solving for. And then how much of the 0.40 molar solution do I need to make? 100 milliliters. Okay. All right, so I'm solving for which variable? V1. So rearrange this formula to solve for V1, and what do you get? M2V2 over M1 equals V1. All right, so now plug in what we have to solve for V1. M2 is 0.40 molar. V2 is 100 milliliters. M1 is 2.0 molar. So go ahead and do that math. And what do you get as V1? 20? 20 milliliters, right? So that's how much of the 2 molar solution I need to measure out. Now, we're not done with this problem, because this question asked, how would we prepare this solution? Not just how much of the 2 molar do we need. So I'm going to walk you through the steps, okay? You would first measure 20 milliliters of the 2.0 molar MgSO4 solution. And you can use a graduated cylinder to do that measurement. You can use a pipette if it's a specific like size pipette. Pipette's going to be more precise, but a graduated cylinder is good enough. When I make solutions for your purpose, like for your use in labs, and even AP, I mainly just use graduated cylinders, okay? Okay. Then we're going to put those 20 milliliters into the appropriately sized volumetric flask. What size volumetric flask are we going to use to make this solution? What do we think? How much of the solution do we want to make? We want to make 100 milliliters. So the only way to make 100 milliliters of a solution is to use a 100 milliliter volumetric flask. So V2 will tell you the size of flask you need. Okay? So we're going to put that into a 100 milliliter volumetric flask. And then we're going to add more of the solvent. We're going to fill to the line, that one line that's on the neck of the flask, fill to the line with the solvent. What do you think my solvent was in this problem? That was my solute. What's almost always the solvent? Water. So unless it states otherwise, you can assume the solvent is water. Okay? So we're going to fill to the line with distilled water. Why are we using distilled water and not tap water? Yeah, tap water has contaminants. There's impurities. Distilled water is one of the most pure waters we can get. So we don't want to add anything to it. We don't want to cause any side reactions or competing reactions. And then the last thing is to mix thoroughly. All volumetric flasks have caps or lids that will go in it. So you'd put the lid on, the cap on, and you'd invert it, or the stopper, whatever you want to call this. You'd put the lid on, you invert it a whole bunch of times, make sure that that solution is nice and mixed, and then you have in this case, you'd have 100 milliliters of a 0.40 molar solution of magnesium sulfate. Okay. So as you finish writing that down, why don't you guys go ahead and start working on number 8 once you're done writing those things down. Number 8 is going to be almost identical to number 7, just different numbers. All right, so as I was saying, 1.0 molar is our M1, 0.020 molar is our M2. We want to make 15 milliliters of that 0.020 molar solution. So 15 is my V2. V1 is what we're solving for. 1,000 milliliters is just the amount of that 1 molar solution that I have available to dilute from. Okay? So, like I said before, you're pretty much always going to be solving for V1. So when we rearrange this formula to solve for V1, we get M2 V2 over M1. Plug in what we have. So what is V1? 0.30 milliliters. Yeah. So this problem actually, we're done technically with this problem because all it asks is how much of that original solution do I need to use. But for the sake of learning this, I would then put this in what size volumetric flask? In a 15 milliliter volumetric flask. You'd fill to the line, guys, with distilled water and mix. Because that's the size of the solution we're making. Yep. Now, if, say we were actually, say I needed to do this in real life. At least here, I don't have a 15 milliliter volumetric flask. The smallest flask size that we have here is 100 milliliters. So I would have to do the calculation for making 100 milliliters of this solution and then just use 15 milliliters of it. Okay? So the only increment sizes we have is 100, 250, 500, and 1,000. So I have to make sure that I plan out, like, what I often do is I figure out how many milliliters of the solution each lab group needs, how many lab groups do I have total across all 3 of my classes, and then I always add extra because there's makeups. Some people get more than they need, they don't know how to read, they don't measure properly, stuff like that. And I kind of like round up to the nearest. Like if I need 675 milliliters, I've got to make at least 1,000. Okay? If I need 490 milliliters, I'm probably going to make 1,000. Or I'll do a 500 and then a 250. Okay? It really just depends though.
I want to see if there's glass or plastic.
It's glass.
Yeah.
All right. Last little bit for this video, and then I'm going to stop it and start recording again for the next one. Last little bit is talking about how these solutions actually form. What's happening on the molecular level, okay? Remember the phrase, like dissolves like, all right? That means two things. The first thing is that polar solvents can dissolve polar solutes and most ionic compounds. A polar solvent like water can dissolve other polar solutes and a lot of ionic compounds. All right, this diagram here is showing how sodium chloride, NaCl, is dissolving in water. Notice that the water molecules are breaking up the sodium ion and the chloride ions. That is called dissociating, okay? So soluble ionic compounds, soluble meaning that they will dissolve in water, dissociate in water. Dissociate means to break up into ions. That's what, if the ionic compound will dissolve in water, that's what it does. It breaks up into ions. So, like dissolves like. Polar solvents will dissolve polar solutes and ionic compounds, a lot of ionic compounds. And then, sorry, I just realized some of you are still writing. So polar dissolves polar, and nonpolar dissolves nonpolar. The diagram that I have shown here is actually not nonpolar and nonpolar. This is sugar, which is a polar molecule, dissolving in water. So this is still a polar-polar diagram. I couldn't find a good one online of like a nonpolar and nonpolar, but it would look similar to this polar and polar. Notice that this sugar molecule, what type of compound is a sugar molecule? It's a covalent compound. This is covalent. Notice that the covalent compound isn't dissociating. It's not breaking up into ions because there are no ions in that covalent compound. Covalent compounds, polar or nonpolar, but covalent compounds do not dissociate. Dissociating is only for ionic. Okay? But the reason that, so this leads us to why oil and water don't mix. Because water is a polar compound. What type of compound is oil? It's a nonpolar compound. So since they're polar and nonpolar, they're not going to mix, okay? Because they don't have similar intermolecular forces. They're different enough, so they don't mix together. They're not going to dissolve in each other. They're immiscible. That's the word. They're immiscible. Okay. So I'm going to stop the video for this one.